Okay, so this course is all about functions, and first let's have a look at the course outline. In the first lesson, we'll cover topic 1. We'll talk about some general concepts about functions, making sure we're using the same language. For example, we'll briefly introduce the concepts of functions, domain, range, graph, x and y intercepts, and so on. And from the second topic, we're talking about different types of functions, such as linear, quadratic, and after the first two topics, I think we have sufficient knowledge to talk about more concepts about functions, such as monotonicity. That means whether the function is increasing or decreasing in some intervals, or parity, whether the function is an odd function or an even function. And after that, we'll continue talking about other different types of functions, such as power functions, polynomials, rational functions, exponential and logarithmic functions, trigonometric functions, inverse trigonometric functions, and then a special type of discrete functions, which are sequences. And at the end of this course, we'll talk about conic sections. Although some conic sections are not functions, they are still important concepts. Okay, any questions? And actually, for each of these functions, we'll have a look at their definitions together with their main properties, such as their graphs, domain, range, x and y intercepts, asymptotes, if any, monotonicity, parity, periodicity, transformation, and the inverse of each type of functions, and so on. Okay, in the first topic, today we're going to have a look at some general concepts about functions. We'll cover these sections. First, we're going to have a look at the overview of some background. So, have you ever heard of the concept of functions?
Kind of.
So, can you describe the definition of functions or what a function is using your own words?
Like you can graph it and it has like I'm not 100% sure.
Yeah, great. So, intuitively speaking, functions or a function is like a machine. Okay, I'll give you a intuitive concept. You don't have to write down everything, okay? It's like a machine. It takes an input and gives us an output. So why should we bother? Why should we learn this? One of the motivation is we want to study patterns in our real life. For example, I set up two examples on the right side. The relation between water bills and your water usage. Probably you already know that the more water we use, the higher the cost, right? So this is some relation. There is some relationship between the water usage and cost. So for example, when your water usage is some number here, you will have a cost here. Some other usage corresponds to some other bill numbers. And if you know the pattern, then you can use this pattern to predict when you have a water usage, what is the cost in the future, right? For another example, phone battery. The longer we use our phones, the lower the battery, right? There exists some sort of relationship between time and battery, right? So probably we notice that one quantity affects another, and sometimes we want a precise way to describe it. So before functions, we might only use tables or graphs, but we need a systematic way to describe each input has exactly one output. This kind of relation is called function. So why should we bother to learn functions? In the summary, first, we want to simplify and summarize patterns. Functions turn complex phenomena into mathematical model. Secondly, we want to predict and apply. Once we know the rule, we can predict results. For example, population growth. What is the limit of growth on Earth? Or temperature changes, or a trend of some sort of phenomenon. Thirdly, this is a foundation for advanced subjects such as calculus, probability, or even physics motions, because we can also use functions to describe physics motions, such as the motions of planets or some other problems. They are all rely on functions. And last, we can develop abstract thinking. We can learn to extract patterns from the real situations and express them with formulas or graphs. Okay, so next, let me introduce briefly the history of functions. So in ancient times, people used ratio and geometric relationships describing how quantities depend on each other. And in the 17th century, two great scientists, Newton and Leibniz, used functions in calculus to model motion and change. And then Euler, in the 18th century, formalized the term function with the notation y equals fx. And nowadays, there are some other applications, for example, Fourier series, set theoretical view, multivariable, and abstract functions emerge. Okay, so what is the rigorous way to define functions? So let's have a look at its formal definition. A function is a correspondence or mapping between two sets x and y, in which each element of set x corresponds to or maps to exactly one element of set y. The domain is set x, also known as independent variable, and the range is set y. Of course, you don't have to memorize this brutally, just pay attention to the meaning. Understanding is much important than memorizing, okay? So we can draw a diagram to illustrate the concept here. Also note that in this course, we only study functions with one independent variable. So we can draw a diagram like this to illustrate the concept of functions. So according to the definition, we have two sets, right? Again, we haven't formally defined the meaning of sets. So now you can just consider sets as a collection or a container, which contains some values. And these values are all distinct. There are no identical values in a set. So you have a set, let's call it x, and we have another set, let's call it y. And for example, we have some elements in set x. These could be numbers, letters, could be anything. So for example, we have three numbers here, 1, 2, 3, and we have three other elements. Let's say, for example, A, B, and C. Then, if the input is 1 in the set X, the output is letter A in set Y, or there is a mapping relation which maps 1 in set X to A to in set Y, and it maps 2 in set X to element B in set Y, and it maps 3 in set X to set C in set Y. So, well, let's give it a name. F is the name of the mapping. So for each input in the set X, there is only one or unique output in set Y, right? So this kind of mapping or relation is called a function. Did you get it? And of course, there might be some other possibilities. For example, we can draw another mapping relation like this. Again, let's call it set x and y by default. Of course, you can also use some other letters, a and b, but we'll just use x and y's here, which are commonly used letters to denote two sets. So in x, we still have 3 elements, let's say numbers 1 to 3, and this time we only have 2 elements in set y. And function f maps 1 to a, maps 2 to a as well, and it maps 3 to b. So again, let's give it a name, f, or we could also use some other letters, g. G is another mapping relation which maps one element in set x to a unique output in set y, right? This is also a function because the left side, the first one is a one-on-one mapping, and the second relation is called many-to-one mapping. But both of the two relations are functions according to the definition. Okay, so let me give you another example. So this time, it is your turn to check whether the given relation is a function or not. So suppose we have 2 sets. Okay, let's use another color here. We have a set x, another set y. Okay, still we have 3 elements here, 3 elements here, and this relation corresponds 1 to a and 2 to a, either a or b, corresponds 3 to c. So this is also a relation, right? It's a relation mapping x to y, but is it a function?
No.
Why?
Because each element of x is supposed to map to exactly one element of y.
Yes, but precisely speaking, not each. There exists at least one input in set x corresponds to 2 different outputs in y, right? If the output is not unique, although it can be called a relation, but it's not a function. So I'll make note here. This is not a function. But it can be called a relation. Okay? Are you clear with the concept of functions?
Yeah.
Okay, and according to the definition, it also gives the definition of domain and range, right? So in the first diagram, the set x is the domain because this is a collection of all the inputs, right? Set y is a range. And be careful, sometimes in some textbooks, the range is also called codomain. And in the second diagram, again, x is the domain and y is the range. And in the third diagram, although it's not a function, we can still call the set x is the domain of this relation. And set y is called the range of that relation, or the codomain. All right, let me know if you finish.
Yeah.
Okay. So next, let's have a look at the notation of functions. So how can we express a function? Apparently, according to this lecture slide, we can use the mapping diagram to express a function, right?
Yeah.
Well, actually, you can use a lot of different methods as long as you can express the mapping relation between 2 sets. Then that mapping relation can be called a function. For example, we have already seen the mapping diagram. So let's write an example here. For example, set x to set y. For example, you have 1, 2, 3, and A, B, C. And then this mapping relation is called a function from x to y, or y is a function of x, right? So mapping table is similar to mapping diagram. You can just draw a table like this. This is x, this is set y. When the input is 1, the output is A. When input is 2, the output is B. When input is 3, the output is C. So this table can also considered as a function, right? Because it's in accordance with the definition of functions. Each input corresponds to one output. And by default, usually we'll use x to denote input and y to denote output, unless otherwise stated. And the third method we can use is called ordered pairs. So in this notation, we can say, well, we'll use the same notation, we'll use different notation to express the same function. So in ordered pairs, we can write it like this. You can say, first of all, we can give it a name. So let's say the name of this function is f. F equals a set of ordered pairs. When the input is 1, the output is A, and when the input is let's just use some numbers. Okay, let's just use the letters here. So I'll modify that later. Okay, when the input is 2, the output is B, and then when the input is 3, the output is C, right? This is another form to express the function, which is called ordered pairs. So in order to use some other notations, let me modify this function a little bit. So this time, let's use some numbers to denote output, not the letters. Otherwise, it's not easy to generate a legit formulas. So let's say 1 maps to 2, 2 maps to 4, 3 maps to 6. Then 2, 4, 6 here, 2, 4, 6 here, right? So this is a third method we can use to describe a function. And we can also use a mapping notation, which is also called arrow notation. In this notation, you can write the function like this. I'll put it here. Okay, we say f column maps x to 2x. And of course, you need to give the scope or domain of the input here, x, right? So we can use this notation here. X belongs to the set that contains 3 elements, 1, 2, and 3. So here, again, they gave the mapping relation name f. The effect of f is to map a input x to output 2x. There is a direction. Be careful with the direction of the arrow. It maps x to 2x. And the input x belongs to the set 1, 2, 3. The set contains 3 elements, 1, 2, 3. This means x can only be the numbers 1, 2, and 3, right? Are you familiar with this notation here? Yeah, you can also write it like this. Or x is between 1 and 3, and x belongs to the integer set, right? They're actually the same thing. Or you could also write x belongs to the interval 1, 2, 3, inclusive both sides, and x belongs to the integer set. Again, they are the same thing, right? But if you have some separated, isolated points, it's better to use this notation here. And formula. So we could also use formula to express functions. This is a commonly used method. So in this method, we could just say fx, again, let's give it a name f, short for functions, fx equals 2x. Okay, this means the name of this function is f, and the effect of this function is to map a input x to 2x. Again, if you use this notation, you have to specify the domain because it's not continuous. It's just the 3 isolated points. 1, 2, and 3. Okay, next equation. Usually in the equation method, we all use a y to denote the output. So we can write y equals 2x. This is called the equation, right? Of course, you can also write like 2x minus y equals 0. They are equivalent, right? And you have an equation in which two sides are connected with using the equality sign here. And again, in this way, usually you need to define the domain. Otherwise, by default, the domain is a whole real number set. Okay, next, graph. So we could also use a graph to express a function. So in this example, there are only 3 points on that function, right? We'll use x-axis to denote the input, y-axis, the vertical axis to denote the output. Oh, so yeah. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And the first point is when x equals 1, y equals 2, which is here, right? And second point is here. Third point is here. So this graph only contains 3 isolated points. And this is a graph of this function. Of course, you can also use graph to describe a function, right? And sometimes this function is continuous. For example, you might end up like a parabola or a straight line. We'll talk about that later. Different functions have different types of graphs. They could be isolated points, or they could be continuous curves. Okay, last, natural language. You can simply use natural language such as English to describe the mapping relation. For example, we could say the output is twice of the input, right? To describe the mapping relation.
Yep.
But do not forget the limitation of your input, and the input can only be 1, 2, or 3. So as you can see here, the formula, equation, and mapping notation are usually the simplest way to express a function, right?
Yeah.
Okay, so are you clear?
Yep.
Any questions?
No.
All right, next, let's have a look at a quick quiz to check your understanding. So given these 4 different diagrams, the question is y a function of x in each mapping relation? Y is a function of x means x is input, y is output, right? So is y a function of x in each mapping relation? When you finish, just give me a shout, okay?
The first one is yes, second one is no, and third and fourth are yes.
Okay, very good, because number 1, 3, and 4 are in accordance with the definition of functions. For each input, for every input, there is only one unique output, right? But
Yeah.
for the second one, there at least exists a point here, for example, corresponds to 2 different outputs, right?
Yeah.
So also, if you have a graph of function, we can use a vertical line check. This is called a vertical line check. To check this relation, check if this relation is a function or not. If there exists at least one vertical line such that there are 2 points of intersection between this vertical line and the graph of the function, then that means the variable on the vertical axis is not a function on the variable on the horizontal axis, right?
Yeah.
Okay, and let's see another quiz. Same graphs, and this time, is x a function of y in each mapping relation?
Yes, no, no, yeah, no. Sorry, yes, yes, no, no.
Yeah, you say yes, yes, no, no.
Yeah.
Is the first one a function or not? It says x of, you think first one, x is a function of y, right?
Yeah. Sorry, no.
No, because, yeah, be careful with the questions here. Careful with the statement here. It says x is function of y, which means x is output and y is input. So when input is 5, you have different outputs. So this is not a function, right?
Yeah.
But only a relation. For the second one, of course, this is a function because it says here x is a function of y, which means for each y, you only have one unique output. So this time we need to use horizontal line check, right?
Yeah.
Each input y corresponds to only one output x. And this makes the fourth one not a function. Because when the input is y, you might end up with two different outputs in the set x, right? Okay, so third one, x is a function of y, which means y is the input. And when the input is 5, output is 2. When the input is 3, the output is 1. And when the input is 2, the output is 1. Is this a function or not?
Yes.
So it's a yes, right? Which makes this one actually wrong. This is not function. Can you see the mistake you made?
Yeah.
Yeah, because this time, if it states y is a function of x here, each input can only correspond to one output. But here we have, when the input is 1, the output is either 2 or 3. So one input corresponds to two different outputs, so it's not a function. No. Okay, so this is a function. This is a function. Oh, sorry, this is not a function. And this is a function. So when we're talking about function, be careful the direction of the mapping relation. Okay? If you change the direction, you might end up with different conclusions. So that leads us to another concept, which is called the inverse of a function. So previously we have talked about there are two different types of mapping relations, right? It could be, for example, F is a 1-to-1 mapping, or it could also be a many-to-one mapping, right?
Yeah.
And if you express this function using diagrams, the arrow of this mapping relation is the direction of the function. So if I reverse the mapping relation, the mapping direction, for example, I use different color to describe another mapping relation which maps A in the set Y to 1 in set X. And the second arrow is also reversed. Third arrow is also reversed. Then the reverse mapping is actually called the inverse of a function, which is usually denoted as f inverse. Okay?
Yeah.
And also for the second type of mapping relationship, second type of function, we could also reverse the direction of mapping. The only difference here is, in this case, the inverse of this function is not a function, right?
Yeah.
So we could say, note that f inverse is a 1-to-1 mapping in the first case, but in the second case, it's a 1-to-many mapping. So in the first case, the inverse of f is still a function. Because it yields the definition of a function, and however, in the second diagram, the inverse of function f inverse, is not a function. Can you see the difference?
Yeah.
All right, and also be careful that f inverse is not necessarily 1 over f. So usually they are different. Okay, be careful with the notation here. If you use a subscript here, f -1, that means f inverse, not the reciprocal of f. Be careful with that, okay? And also, for the original function, we know if we have an arrow direction like this, then it maps any element in set x to an element in set y. We call x is the domain of the original function f, and y is a codomain or range in both cases. Can you recall that?
Yeah.
And if you reverse direction, then for f inverse, the range of the original function is the domain of the inverse, and the domain of the original is the range of the inverse. Does it make sense?
Yeah.
Because domain is a collection of inputs, range is a collection of outputs. Okay. Any questions?
No.
All right, so let's make a summary here. A function is 1-to-1 if there's only one value of x for each value of y. It's a many-to-1 if there's more than one value of x with the same value of y. The inverse of a function f is the reversed mapping relation, usually denoted by this notation here, f inverse. And be careful that the inverse of a function is not necessarily a function. You need to check whether each input corresponds to only one or unique output. Okay, it must yield the definition of a function. And function y equals fx has inverse function y equals f inverse of x if and only if it is 1-to-1. So here, if and only if means this. The two statements on both sides of the arrow are equivalent. Many-to-one functions do not have an inverse function. Okay, so be careful with the concept of the inverse of a function and inverse function. Sometimes they are different. Okay?
Yeah.
All right, let me know if you finish. Okay, I'll put a note here. The inverse of a function, and there's another concept called inverse function. They are not necessarily the same. Okay, if you're done, let's have a look at. Yeah, we have talked about this before. The inverse of function has range equal to the domain of fx, and the inverse of function also has domain equal to the range of fx. Actually, everything's reversed. Okay? Any questions?
No.
Alright, then next, let's have a look at how we can determine the domain and range of a relation or a function. So first, let's talk about the domain. The domain is a collection of all possible inputs, right? So if you want to find the domain, you are actually try to find a set of all possible inputs. Then we should consider if there is any restrictions of the for the inputs. So consider the restrictions of the input. Okay, in this course we'll only talk about functions with real valued inputs. So by default, if there is no restrictions, we say the domain is just the whole real number set. Alright? Otherwise, it's a subset of the real number set. So where does these restrictions come from? It can come from, one, the expression itself. The expression of the function itself. Okay, for example, if you have a function like this, y equals the reciprocal of x, in real number set, we cannot use 0 as denominator, right?
Yeah.
So the domain is x belongs to the real number set, x cannot be 0, right?
Yeah.
Or strictly speaking, you should use a set notation here. So you could say this is a set of x such that x belongs to real numbers set and x is not 0. And for another example, if you have y equals the positive square root of x, then again, in the real number set, we do not take the square root of any negative numbers. So in this case, the domain is a set contains all values expressed in x. X is greater than or equal to 0. Right?
Yeah.
Or you could also say x belongs to the set from 0 to positive infinity. They are the same thing. Right?
Yeah.
So are you familiar with both of the notations?
Yeah.
Okay. And in some textbooks, you could also see these expressions. You could just say x is greater than or equal to 0. This is sometimes acceptable, but not very rigorous. Okay, acceptable, understandable, but not recommended. And secondly, the constraints or restrictions can also come from the real world. So what does this mean? This means if you want to model the real world, sometimes you need to consider the restrictions for the inputs. For example, if you have a pizza with radius r, then the area A is given by pi r squared, right?
Yeah.
And because it models the area of a pizza, then by default we know r must be greater than or equal to 0. So this restriction is not from the expression of the function itself, but from the real world. Or could just state that r belongs to 0 to positive infinity. Or sometimes it's not actually positive infinity, right? Sometimes you should give it a maximum number. Also a restriction from the real world. As for the range, you need to calculate all possible values of the you need to consider all possible values of the output. And sometimes you could make use of the graph of that function to help you analyze all possible values of the output. Sometimes you need to analyze the expression of that function. And again, if you're not familiar with different types of numbers, here is a good diagram you can have a look. Just give it a quick review, okay? So the smallest number set we usually use is called the natural numbers. But be careful that the natural number set has different definitions in different books. You should use context to help you decide its exact meaning. For example, some people believe the natural number set starts with 0, or others believe it starts from number 1. I'm not sure which notation you are using in school. Which one do you use in school? The natural number set starts with 0 or 1?
0.
0? Okay, so you could stick to your definition taught in school. But to be clear, usually if you believe that starts with 0, usually we'll use this notation n0 or n subscript 0 to specifically point out that the natural number set you are using starts with 0, okay? And use n1 or n star or n plus, these three notation, to denote natural number set without 0. Okay, and natural number set is closed to addition operation, right?
Yeah.
Which means if you pick two arbitrary natural numbers, add them up, and then the new number is also within the natural number set. So apparently this is not sufficient to describe subtraction, right? So in order to make it closed for subtraction, we introduced the integer set, right? The integer set contains any number that can be written without a fractional component, such as -3, -2, -1, 0, 1, 2, 3. It's the natural number set plus all the negative integers. And this is still not sufficient to be closed to describe quotient, right? Therefore, we introduced the rational numbers. The rational numbers can be expressed as a over b, when a and b are integers and b is not 0. The rational number set includes and only includes finite decimals or infinitely repeating decimals. For example, -3 over 5, -7 over 5, -1, 0, 1 over 2, 4 over 3, 5, something like that. And a larger number set is called real numbers. Real number is a limit of convergent sequence of rational numbers, a value of a continuous quantity that can represent the distance along a line. So that means real numbers corresponds to the different points on the number axis. So by default, in this course, we only consider problems in the real number set. We do not touch the imaginary numbers or the larger set complex numbers. Real numbers is a type of complex numbers, but without the imaginary part. So we only consider real numbers in this course unless otherwise stated. Okay? And these are the commonly used symbols to describe each of the number set. So make sure you're familiar with numbers here, symbols here. Okay? You finished?
Yep.
Okay, so next let's have a look at an example to check your understanding of what we have learned so far. So you're given a table here. Determine the domain range of each relation. So the table describes some sort of relation, corresponds to from age to number. Use domain and range to determine if the relation is a function. Table is for number 2. Number 1 is just some ordered pairs, which is also a relation, right?
Yeah.
So I'll give you 2 minutes. When you finish, you can let me know, okay? And you can compare result with mine.
The first one is not a function, and the domain is from -3 to 6.
Okay. All right. Let's have a look at solution for the first one. All right. The domain. Domain is a collection of all the inputs, right?
Yeah.
Also note that they are isolated points. So usually we don't say from to, because from to means every point in that interval, right? So yeah, we say it's a set that contains 1, 2, 3, 4, 5 numbers, which is -3, 5, -2, 5, and 6, separated by commas. So now you can see that actually. Okay, let's consider range as well. The range is also a set that contains 5 numbers, which are 4, -6, 7, 3, and -8. As you can see here, same input corresponds to different output. So that means this is not a function, just a simple relation, right?
Yeah.
So it's not a function. Okay, for the second question, have you finished that?
Yeah.
The method should be the same, right?
Domain is 4, 5, 6, 7, 8, 9, 10.
Yes, domain is a set. You could list all these separate sets, and you could also say it's a set of all x such that x is between 4 and 10, and x belongs to the x-intercept. You could also write it in this way, right?
Yeah.
And the range Well, we could not use a simple notation, so it's a set, just list all the numbers, that's fine.
9, 11, 12, 14, 8, and 22.
Okay, and make sure you use a pair of parentheses to denote the set, and a set cannot contain identical elements. If you have identical elements, just keep one of them, okay?
Yep.
So is this a function?
Yes.
Yes, because every input is different. So this is a function. All right, any questions?
No.
Okay, then let's consider another one. So this time this function is expressed using a formula, right? Name of this function is f. It maps x to square root of x plus 3. So can you determine the inverse of that function? And then state the domain and range of the function and its inverse. Again, let me know if you finish, okay?
The inverse is f negative 1 bracket x equals square root of x plus 3.
Okay, have you finished?
Yeah.
Okay, you can compare result with mine, okay? Okay, first of all, if you want to determine inverse of the function, that means you should give the expression of the inverse of that function, right? So for that purpose, usually we'll use the letter y to denote the output. We could let y equals the input. Input is x, so let y equals square root of x plus 3. This is the original function, right?
Yeah.
And you need to find the expression. Well, original function somewhat corresponds to x from x to y. So you need to find the expression that corresponds to y to x, which means you need to solve x in terms of y, right?
Yeah.
Okay, so in that purpose, we could square both sides. So we have y squared equals x plus 3, right?
Yeah.
So note that we want to solve x in terms of y. So x equals y squared minus x, right?
Yeah.
Okay, usually we'll use x as input and y as output. So, but in this case, this is our output. This is our input, right? Mm-hmm. So in the last step, usually we'll interchange the position of x and y. According to convention, you could conclude, therefore, the inverse of the inverse function is actually y equals x squared minus 3. We interchange the position of x and y because usually we'll use x to denote the input, y denote the output. Or you could also say f inverse of x equals x squared minus 3. This is a function you're looking for, right?
Yeah.
Okay, now let's consider domain and range of the function and its inverse. So in order to find domain and range of the inverse, first you need to find the domain and range of the original. So we could say consider the original function. Name is f, which is y equals square root of x plus 3. We can easily see so find domain. We can easily see there is a limitation for the x, right? X plus 3 must be greater than or equal to 0, right? And this is equivalent to x must be greater than or equal to -3, and therefore we say its domain is x belongs to -3 all the way to positive infinity. This is its domain. So how about its range? So we'll talk about this type of function at a later times. Now, can you give it a reasonable guess? What is the possible outputs of this expression?
Not sure. Maybe.
Well, we have already determined x plus 3 is greater than or equal to 0, right? So if we put a number that is greater than or equal to 0 under a square root symbol, can you make a guess what is the possible range?
The square root of x is greater or equal to 0.
Yes, it's still a number that is not negative, right?
Yeah.
And actually can cover all the numbers on the positive side of x together with 0. So the range is actually 0 to positive infinity as well. So we'll talk about this type of function later. So as long as you can guess the range at a current time, you'll be fine. So this is the domain and range of the original function. Now you can directly find its domain and range according to the original function. Then we know let's say, then we know for the inverse, we'll use letter F inverse. We also know its expression, which is x squared minus 3. Of course, you could also say the inverse is expressed as y equals x squared minus 3. Both of the two expressions are acceptable, okay? And the domain is x belongs to -3 all the way, the domain of the inverse is the range of the original, right? Yeah. So in this case, the domain is x belongs to 0 to positive infinity, and the range is y belongs, okay, we forgot a y here. Y belongs to the interval from here, -3 to positive infinity. You get it?
Yeah.
Okay, have a look at this question. Make sure you are clear with everything.
Okay.
All right, let's have a look at a similar question. This time you need to solve this independently to check your understanding on how to determine the inverse and domain and range of the original and its inverse. Okay, let me know if you finish, and you can compare your result with mine. Yeah, this time we have another different type of function. This is actually called a linear function. We'll talk about linear function in our second lesson. But here, it doesn't matter if you don't know the properties or anything about the linear function. You could just use the expression to find its inverse and domain and range, right?
Okay.
Okay. Let's have a look at solution together. Okay, so this time you are given another function. It maps x to 1/3 of x minus 8, right?
Yeah.
So it asks you to find the inverse domain and range of both of the two functions. So we can solve this problem all together. So we can first let y equals, well, you could also say f maps x to y such that y equals 1/3 x minus 8. First, let's find its domain. Domain is the set contains all possible inputs. Is there any constraints for the input x here?
No.
No, so the domain is a real number set, right?
Yeah.
You could also say the domain is from negative infinity to positive infinity in the set notation like this. And how about the range? Range is a set contains all possible outputs. So if you have any arbitrary real number here, divided by 3 minus 8, can you imagine what is all possible outputs?
They're all possible.
So it's could also be any real number, right? So it all spans to the whole real number set. Again, you could also say from negative infinity to positive infinity. Well, usually we write it like this, but sometimes you could just omit the x and y's. That's fine. It doesn't affect understanding. And then, if y equals 1/3 of x minus 8, we have 3y. We can multiply both sides with a 3, right?
Yeah.
Equals x minus 24. So remember, in order to find the inverse notation, the original maps x to y. In order to find the inverse, you need to find x in terms of y, to solve x in terms of y, right?
Yeah.
And next we have x equals 3y plus 24. Okay, so this is the expression of the inverse, right? But again, usually we'll use x to denote input, y to denote output. So we can make this conclusion here. F inverse is y equals 3x plus 24. So in this expression, we use x as input, use y as outputs. Basically speaking, in the last step, change your x and y, change their positions, okay? Or you could also say f inverse x, well, directly write f inverse of x equals 3x plus 24. This is also acceptable. And now the domain of the inverse is the range of the original. So it's a whole real number set R. And the range of the inverse is the domain of the original. So it's also the whole real number set R. So by default, we talk about problems in the real number set R. Okay, are you clear now?
Yeah.
So in a summary, if you are given arbitrary types of functions, you should be able to find the inverse and state the domain and range of the function and its inverse, okay? So as to some other properties of the inverse and the original function, we'll talk about that in our second lesson, okay? For example, we can prove that the graph of the original and the inverse are actually symmetrical with this line, y equals x. So we'll talk about something like this in our second lesson. So we'll just leave it here, okay? Because that involves some properties of lines. We'll talk about in the second lesson. Okay, next let's have a look at another quiz. Given a function fx which maps x to x squared plus 3x minus 3. So this is a function. There's another function gx equals f inverse of x, which means gx is the inverse of fx, right? A possible value for g1 is which option? A, -4, B, 0, C, -1, and D cannot be determined. Any thoughts? So have a look at this practice and let me know when you finish, okay?
Is it A?
Yeah, that's so. Can you show me your method?
I plugged in 1 as one of the possible values, so 1 equals x squared plus 3x minus 3, and then I solved that and I got x could equal or negative 4, so it's A.
Yes. So correct option is A, right?
Yeah.
Yeah. This question really checks your understanding of a function with its inverse. So G1 is actually if you want to find G1, you're actually trying to find f inverse of 1, right? So suppose we let f inverse of 1 equals, we don't know that number, so suppose that number is A, which means somehow the inverse of f maps maps 1 to A, right? Or in other words, the original function maps A to 1, right?
Yeah.
Okay, so we know when the input is A, the output is 1, so we can just insert A into the original function. So A squared plus 3A minus 3 equals 1. So that means A squared plus 3A minus 4 is 0. Then we can factorize the left side, which is A plus 4 times A minus 1 is 0. So there are two possible values for A. One of them is negative 4 and the other one is 1, right?
Yeah.
Okay. Is there any other ways to solve it?
Get the inverse.
Well, method 1 seems simple enough, right?
Yeah.
But a more generic way is actually if you want to find a value or image at some point for a function, you could just find the expression of that function, right? If you know the expression of that function, then you can calculate every image of every point, right?
Yeah.
So the second method is to, what if we find the expression of f inverse? Okay, you can find f inverse by letting y equals x squared plus 3x minus 3, right?
Yeah.
Then in order to find the inverse, we need to solve x in terms of y. Are you able to solve it?
I got x squared plus 3x equals y plus 3.
Yeah, we could use completing the square method, which you learned from the algebra lessons, right?
Yeah.
So by completing the square, we have the right side transformed to x plus 2 over 3 squared. And if you expand this, you will get x squared plus 3x plus 9 over 4. We don't have 9 over 4, so just compensate that by add a negative 9 over 4. Then copy the rest of that expression. We have a negative 3 here, right?
Yeah.
Okay, in this way we can easily separate x and y. So this gives us y equals x plus 3 over 2 squared minus, then we have 21 over 4, right?
Yeah.
Which means y plus 21 over 4 equals x plus 3 over 2 squared. So this means x plus 3 over 2 is either positive or negative. Do not forget the negative symbol. Y plus 21 over 4, right?
Yeah.
And then x equals negative 3 over 2 plus or minus square root of y plus 21 over 4. So the inverse function is y equals negative 2 over 3 plus minus x plus 21 over 4. So this is the expression of the inverse, right?
Yeah.
So if you want to find the output of 1, just simply insert 1 into that expression, which you end up with y equals negative 4 or y equals 1. These are the possible outputs, so we can only choose A, right?
Yeah.
These are the two methods you can use. Apparently method 1 is much simpler. Any questions? Okay, next is a very simple concept, evaluating a function. Given input, insert that into a function machine, then you have an output. So this process is just called evaluating function. And for example, if you insert a into that function, you will get fa, right? Then fa is called the image of a. Very clear? Okay. For example, if you see a question like this, given the expression of fx, which is fx equals 2x, and if question asks to find to evaluate f5, then we simply insert 5 into that function to get the image of 5. So f5 is simply 2 by 5, which equals 10, right? This is a process called evaluating a function. Okay, let me know if you finish. All right?
Yeah, done.
Okay, then next let's talk about the concept of the graph of a function. Okay, in this course, we only talk about the graph of real valued function of a real variable. By real value, a real variable function, I mean the domain is real numbers. Real value function means the codomain or range is also real numbers, or a subset of real numbers. And real valued function of real variable means both domain and codomain or range are real numbers or subsets of real numbers. It takes a real number as input and produces a real number as output. Then, the graph of such a function is actually the set of all points in the Cartesian plane corresponding to the input-output pairs. Then, if you only consider single variable functions here, it's actually all points in the 2D Cartesian plane, right? So we could use a graph on the 2D Cartesian plane to describe a function. So graph of f is actually a set of all pairs of a set of points whose x coordinate is x and y coordinate is fx, for x belongs to the real number set. And the x coordinate represents the input or the independent variable, and y coordinate represents the output, which is a value of that function. For example, again, let's consider this function y equals 2x, and the graph of this function is actually a line. Well, this is a linear function. We'll talk about linear function in our second lesson, and this is not hard to guess, right? When x is 0, y is 0, and as x increases, y increases proportionally, so it's actually a line which crosses the origin point. So when you draw the graph of function, usually we put the equation of that function next to its curve. So this is y equals 2x. The graph of function again is a collection, a set of points that satisfy the equation of that function. This also applies to equations which involves only x and y, such as conics, although sometimes they are not functions. For example, you could also draw the graph of conics such as x squared plus y squared equals 1. So what does this look like? Can you recall what you have learned in algebra? What does this graph look like?
It's a curve.
What kind of curve?
Like a parabola, so...
A parabola has something like this. Y equals ax squared plus bx plus c, where a is not 0, right?
It might be a circle.
Yeah, it's a circle because first one, if you square both sides, this first one is actually the distance between x, y to the origin point. And if that distance is constant number 1, that means it's a collection of all points whose distance to the origin point is constant number 1, so it's actually a circle, right? Again, although this is not a function, if you consider all x and y points, all x and y pairs, this is not a function but a conics, but still we can draw its graph on the 2D Cartesian plane.
Yeah.
So the graph of function or a equation is actually a collection or set of all points that satisfy that equation. That's a graph of function. And there are also some trivial concepts. First, the x-intercept. So x-intercept is a point. So this is its formal definition. It's actually a point where the graph of function or relation, so it could also be a relation such as x squared plus y squared equals 1. So this is a relation of the function, intersects with x-axis. So that means no matter what the graph look like, for example, let's just write some arbitrary graph here. No matter what the graph looks like, as long as you can find the intersection between this curve and x-axis, these points are called x-intercepts, right? let's say the x coordinates are -1, 1, 3, and here we have a point 0, 2. So in this case, the x-intercepts are, okay, according to the definition, they are points, right? So technically speaking, you should specify both the x and y coordinates. So the x-intercepts are -1, 0. Second point is 1, 0. And third point, well, third point is 3, 0, right? These are the x-intercepts. However, we could also simply say the x-intercepts are x equals 1, -1, 1, or 3. Or even much simpler, you could just say the x-intercepts are -1, 1, 3, when there is no confusion. Because by default, we know the y coordinate of the x-intercepts are always 0, right?
Yeah.
Okay, and we also call these values zeros or real roots of that function. Okay, I'll make a note here. We also say the real roots of zeros are x equals -1, 1, 3, or sometimes simply speaking -1, 1, and 3. These numbers are also the real roots or zeros of that function. Be sure you know these notations as well, okay?
Okay.
Alright, in a summary, these are the key characteristics of all the x-intercepts. Location. The x-intercept is always on the x-axis. These points are called x-intercepts. Secondly, the y-coordinate of an x-intercept is always 0. Then it's written as a coordinate pair, x0, and sometimes simply write the x coordinate of that point. And last, the real roots or zeros of such a function or relation are the x coordinates of these x-intercepts. Okay, any questions? And also note that if I change the name of the horizontal or vertical axis, for example, if you use letter R to denote the horizontal axis, then it's better not use the x-axis. So in this case, we call it R-intercept. You get it?
Yeah.
Because the name of the independent variable becomes R here. So we say R-intercept, not x-intercept.
Okay.
And similarly, we can have the concept of y-intercept. Y-intercept is a point where the graph of a function or relation intersects with y-axis. Okay, for example, no matter what the graph looks like, this point is called the y-axis, the y-intercept, right? Okay, so let me ask you a question. Can we have three options? Can we have 0, 1, more than 1, x y-intercept. So what's your opinion? Can we have 0 x-intercept? And similarly, can we have 0, 1, or more than 1 y-intercept?
Yes. We can. I think we have 0 x-intercepts if you have like the horizontal line.
Which one are you talking about? Can we have? Okay, let's say 1, 2, 3, 4, 5, 6. 6 questions. How about the first one? Can we have 0 x-intercept?
Yes.
Yes. Because sometimes the curve does not intersect with x-axis, right?
Yep.
Can we have 1?
Yes.
Yes. Only touches the x-axis once. More than 1 is also okay, right?
Yes.
How about y-intercept? Can we have 0 y-intercept?
Yes.
Yes. Sometimes the curve does not intersect with the y-axis. In that case, we have 0 y-intercept. Can we have 1?
Yes.
Yes. Can we have more than 1?
Yes.
Are you sure?
If it's...
What if you have 2 y-intercepts?
No, you can't. Then no, you can't.
You can't. Otherwise, for the same input 0, you will have 2 different outputs, right?
Yeah.
So be careful. It also checks your understanding of functions. So we cannot have more than 1 y-intercept for a function. Okay, we're talking about function, not relation. Alright, in a summary, the key characteristics of y-intercept are as follows. First, the location is always on the y-axis. Second, the x-coordinate of a y-intercept is always 0. Then it's written as a coordinate pair 0, y, or sometimes just y itself. Then a function cannot have more than 1 y-intercept. Okay, have a look at these and let me know if you finish.
Yeah, I'm done.
Alright, let's have a look at a quick quiz to check your understanding. Can you find the x and y-intercepts of the function y equals x plus 2? Then state the zeros of this function.
The y-intercept is 2.
Sometimes we write y-int for short.
Okay.
It's 1x is 0, right?
Yeah, so 2.
So you can just state 2 or 0, 2. How about the x-intercept?
Is negative 2.
Negative 2. Or sometimes negative 2, 0. Okay, how about zeros?
Could you explain what that means again?
0 means what kind of value of x can make this function be 0?
Oh, 2.
Negative 2, right? Or it could also say x equals negative 2. Okay?
Okay.
Alright, next trivial concept is about graph of function is asymptote. Sometimes when you see the word asymptote, that means a line that the graph approaches or begins to look like as it tends to infinity in a particular direction. So we'll try to formally define the asymptotes in another course called calculus. But for now, as long as you have an intuitive feeling, that's fine. Okay. For example, in this diagram, when x approaches this line, the function approaches negative infinity, so it will get closer and closer to the vertical line here, but never touches that line. So in that case, we say this line is a vertical asymptote of the graph of this function. Similarly, if you consider this direction, when x approaches positive infinity, y approaches, let's say, a, then this line is called horizontal asymptote. The curve will get closer and closer to that line as x approaches positive infinity, but it will never touch it. It will never touch it. So this line is called horizontal asymptote. And usually to find vertical asymptotes, we look for values of x for which the function is undefined. And then to find horizontal asymptotes, we usually consider the behavior as x approaches either positive infinity or negative infinity. Again, these are not rigorous definitions. It's only an intuitive way we consider asymptotes. We'll talk about the rigorous definition in our calculus class, okay?
Yeah.
Alright, if you don't have any questions, let's consider a quiz. Can you try to sketch a graph of this function? Okay, we haven't talked about what type of the function is. It's actually called a power function. But can you give it a reasonable guess? What does this graph look like?
Do I just draw on your screen or?
Yeah, you can just draw on the screen. Well, if you draw the sketch of the function, it don't have to be that precise. As long as you can draw the overall shape, that's fine.
Oh, okay. I think it's like this. Or like this. Oh, sorry. Bad. That?
Yes. So there are two branches, right?
Yeah.
So suppose this is.
Oh, sorry.
No problem. I'll just help you draw it. So let's call this vertical axis as y, horizontal axis as x. So we can analyze n behavior to find the overall shape. So first of all, x cannot be 0, right?
Yeah.
So there won't be any y-intercept. And when x approaches positive infinity, this is a very large positive number. 1 over a very large positive number will give you a very small positive number, which is near 0 but never touch 0, right? Y approaches 0 from the positive side. We use this notation to say y approaches 0 but from the positive side, which from this side. So there must be a branch and behavior like this. And also when x approaches 0, but from the positive side, which means from this side, you will have a very small positive number here. 1 over a very small positive number, such as 0.00001, will give you a very large positive number, right? So in that case, while y approaches positive infinity, right?
Yeah.
So that'll give us one branch like the one you draw here. And similarly, in the third quadrant, when x approaches negative infinity, which is from this side, we know you will have a very small negative number here, so y approaches 0, but this time from negative side. Therefore, you have this branch here. And when x approaches 0, but from the positive side, from the negative side, y will approach a very small negative number, which is negative infinity, right? Therefore, we have another branch here. Actually, they are symmetrical. They have a point symmetry with the origin point. We'll talk about this later. It's a simplest form of a rational function. We'll talk about rational function in our third or fifth lesson. Like I said in the very beginning here, in topic number 7, we'll talk about rational function. So this is a type of simple rational function. We can easily analyze its graphs. Okay, let me erase this first. Erase. Okay, basically this is this covers all the concepts in the first lesson. Let me give you another quiz. Okay, let's make a summary first. So in the first lesson, we have talked about why should we learn functions, right? And the formal definition of functions, which is actually a mapping relation from one variable in the set x to another variable in set y. Usually we'll use x as input, use y as output. So function is actually a mapping relation, right?
Yeah.
And notation function, we have also talked about different notation of functions. You could use either a mapping diagram, a formula, a mapping notation, and a table, or even natural language, right? Inverse of function. So if you have a function f which maps x to y, the inverse of a function is denoted as f inverse, which maps y back into x. So it's just the inverse process of the original mapping. And the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. They are actually opposite, right?
Yeah.
Okay, we also talk about evaluating a function. This is actually a process of giving a input to the function machine and find its output. And the output is also called the image of a function. So in that case, the range of a function is actually the set contains all the images of the inputs. And last, we talk about the graph. Definition of a graph, a real valued function of a real variable. The graph is actually a set of all points that satisfy the expression of the function, or just they satisfy the function expression, right?
Yeah.
We have also talked about how to find, given a function, how to find its inverse. Okay, so last, let me give you a practice. To check your understanding. So given a function fx equals square root of 2x plus 1, can you find the inverse of fx and then state the domain and range of fx and its inverse? Okay, let me know if you finish, alright?
Okay. Okay, I'm done.
Okay, let's have a look at the solution together. Find the inverse of fx means you need to solve x in terms of y, right? So first of all, we can let y equals square root of 2x plus 1. That's the original function, right? So here, it's better to find the domain and range of the original function. The domain of the original function is, well, let's say find the domain. So we could let x plus 1 must be greater than or equal to 0, right? Then we have 2x is greater than or equal to negative 1. And then x must be greater than or equal to negative 1 over 2. So the domain is the set from negative 1 over 2 all the way to positive infinity, right?
Yeah.
Okay, then find the range. So basically you have a non-negative number here. The square root of a non-negative number is also any non-negative number, right? So we could directly say the range is from 0 to positive infinity. And then we can find the expression of the inverse. So next we solve x in terms of y. So in order to do this, we can square both sides. Y squared equals 2x plus 1. And note that we have y squared minus 1 equals 2x, and then x equals 1 over 2 times y squared minus 1. That's the expression of the inverse, right? But usually we'll use x as input, y as output. So we say f inverse has this expression. It's y equals 1 over 2 x squared minus 1, right?
Yeah.
The domain is the domain is the range of the original, so you don't have to calculate this again. The domain of the inverse is just the range of the original, so you could directly say the domain is from 0 to positive infinity, right?
Yeah.
And the range is the domain of the original. Again, you don't have to calculate this again, just copy the domain here. That's the range. That's the range of the inverse.
Okay.
Okay, is the inverse a function?
Yes.
Yes, because for every x, there's only one y corresponds to that, right? Okay. I'll send you the homework Google Classroom.